am the very model of a modern nature general. Live information, vegetable, animal, and mineral. I know the kings of England, and I quote the facts historical from Marathon to Waterloo in order categorical. I'm very well acquainted too with matters mathematical. I understand equations both as simple and quadratical. About binomial theorem, I'm teeming with a lot of news. Lot of news. Got it. With many cheerful facts about the square of the hypotenuse.
All right, this is the third and final part of our Math 140 review. This is the stuff since the second exam. We start looking at areas and integrals, specifically with Riemann sums. So an important thing to remember is that Riemann sums approximate integrals with rectangles. So if we wanted the integral, the area under some curve between A and B, we say, instead of doing the integral of f of x dx, we approximate that by a few rectangles, something like that, and we just calculate the area of those rectangles and we say that's an approximation. And this particular one I've drawn would be the L5 approximation. The 5 meaning we're using 5 intervals, 5 rectangles. The L meaning we're using the left endpoints of every interval. So if you look like that, we take the point on the left of the interval and draw a straight horizontal line to the other side, and that's what determines the height of our rectangles. So you could have an R5 estimate, an R2 estimate. Midpoint estimates are also possible, but we mostly focused on left and right hand estimates in terms of Riemann sums. Next big topic was antiderivatives. This is just do the derivative backwards. So if you have x to the n, the antiderivative, increase the power by 1, then divide by that. And don't forget to put a plus c at the end. An important concept to remember is that there's no quotient rule or product rule for antiderivatives at all. So if you have something that looks like you should be using a quotient rule on it, what you really need to do is change that into fractional powers before you do the integral. The proper definition of a definite integral from a to b of f of x dx, is this limit as n goes to infinity, a limit of a sum of f of a plus I b minus a over n times b minus a over n. And you can think of that as limit as n goes to infinity of the sum of f of xi delta x. So this is the same as a Riemann sum taken to infinity, where xi is a function, either a left or right hand endpoint estimate. Delta x is the width of the rectangles. If you take the limit as you get infinite rectangles, you'll get the exact integral. In terms of which functions you can take integrals of, all continuous functions are integrable. The one that people forget, jump discontinuities are integrable as well. Vertical asymptotes, another kind of discontinuity, are not integrable. So if you have your function going off to infinity, you can't calculate the area under that. When you're doing some of these, just find the integral problems, it's important to remember that integrals are just areas. They represent areas. So if you have something that looks like integral from 0 to 5 of square root 25 minus x squared, you can try to do a substitution or something on there, but you're not going to be very successful until you realize that this is just a circle with equation x squared plus y squared equals 5 squared, and your integral from 0 to 5 represents the quarter of a circle. So you know the formula for area of a circle, pi r squared, divided by 4. So your answer is just 25 pi over 4. We had a very good lecture on fundamental theorem of calculus, but the upshot of that was if f of x is defined in terms of an integral, then the derivative of that function is just g of x. So you take the x and plug it into g, and you're done. If the upper limit of integration is a function, so going from the integral from a to h of x of g, you plug to find the derivative, you plug the h into g, then multiply by the inner derivative, which is just h prime. Substitution rule. You use this when the inner derivative of a function appears in the integral. So something like sine of square root x over square root x dx, the derivative of the inner function, so derivative of square root x is 1 over 2 root x, so that 1 over root x appears in the integral, so that makes you pretty confident you can use the substitution rule. Also, something like integral of tangent cubed secant squared, we know that secant squared is the derivative of tangent. We know that for tangent cubed x, the cubed is the outer function that makes tangent the inner function. So the fact that secant squared appears inside the integral should make us comfortable with that as well. So let's just continue these two examples. If we call u equal to the square root of x, then du is 1 over 2 root x dx. It's usually a good idea just to move the constant to the other side, and then that makes this integral 2 integral of sine u du. The second example, here we say u is equal to tangent, and like we said, du is secant squared. We don't have a constant here to move to the other side, so our integral of tangent cubed secant squared just turns into integral of u cubed du. And of course, when you have definite integrals with limits of integration, you need to change those to be in terms of u as well. Really brief on symmetry. If you have an even function, then and you integrate it from negative a to a, some symmetric integral, symmetric about 0, then you can just do the integral from 0 to a and double it. And if you have an odd function from negative a to a, do the integral from negative a to a, you just get 0. Spent a little bit on area between curves. Let's say we want the area between these two curves. One is called y1, one is y2. You want that area. First of all, you need to find out where they cross, so you set y1 equal to y2 and find those points in terms of x. Let's just call those a and b. Then the area is integral from a to b of upper curve minus the lower curve. The last big topic was volumes or solids of revolution. And the way to do these problems are try to sketch the area, decide whether to integrate with dx or dy, and then at the end choose to use disks, washers, or shells. So I'm going to throw up an example here. Say we have two functions f and g that are functions of x, and that they cross at a and b. And so as before, as with area between curves, you may have to set those functions equal to each other to solve for a and b. So if we wanted rotate the volume of the solid formed by rotating this region about y equals -5, so put y equals -5, some axis of rotation down there. You need to consider an element with dx, and say we want to integrate dx because we have f and g as a functions of x. That would mean that we're using washers. The generic equation for a washer would be pi outer radius squared minus inner radius squared dx, where the outer radius is the distance from the axis of rotation to the top of the element, which in this case would be f plus 5. The inner radius is the distance from the axis of rotation to the bottom of the element, which in this case would be g plus 5. If we wanted to rotate the region about the line x equals -3, so a vertical line, Here, we use the same element, but here we're using shells, the shell method, and the general formula for that would be integral of 2 pi RH dx. And this r has nothing to do with the r out, r in from above. In this case, r is the distance from the axis of rotation to the element, and that's in terms of x. So most of the time this ends up being pretty simple. So in this case it would be, that's the distance, it's just x plus 3. H is just upper curve minus lower curve, so it's the height of the element, which you can just say is f minus g. Those kinds of problems I recommend getting a lot of practice on, but that is it for solids of revolution, and that's actually it for the semester. So thanks, it's been a good semester. Good luck on the final. We'll see you next time.
I'm very good at integral and differential calculus. I know the scientific names of beings, animal killers. In short, it matters vegetable, animal, and mineral. I am the very model of a modern major general.